welcome to the 31st lecture. I think last lecture I said it was the 20th. So
we've had 10 lectures in the last 4 days.
I know. Yeah, something like that. Okay, and I seem to be talking today, so let's see what we've got to talk about.
Record, Rog.
I am recording.
Well, it's not, the button isn't showing on my screen.
Oh, well, it's yeah, well, you can record your own if you want.
No, usually it shows when you're recording.
Yeah, but it's up there saying recording, so it must be doing that.
Okay.
Okay, so now, can you see that?
Yep.
Yeah, that's all right, is it? How do I make that full screen? Like that. Okay. I don't know what this green thing is. I don't know how to get rid of that. Anyway, you'll have to put up with a green line down the middle. Can you see a green line down?
Yeah, I think it's telling you what's visible on some people's screens.
Oh, right. What do I do about that?
Well, change your screen size. I don't know.
Well, okay. You just I'll make it a bit smaller actually. I think
that's good.
Yeah, okay.
That's good.
So what have we got here? 3 trefoils, 4 trefoils. Well, 5, I suppose. Now the one on the left is just an immersion of a circle in the plane. And essentially it's dead, okay? I'm going to shut everybody up, I think. I can't do that. I'll do that. I'm going to shut everybody up. Mute all. Okay, go back to sharing the screen. Right. Okay, so the trefoil on the left is dead. It's just an immersed curve in the plane. It comes to life as we go to the right. So what I've done to make it come to life, or to give it the appearance of life, is to do something to all the crossings. In this case, the standard thing we do is to break the undercurve and continue the overcurve. And I will call that a glyph. Okay. And if I do it the other way around on the third one along, you can see it's the unknot, which is different from that one. And then over here, we've got yet a 4th one, which has got a virtual crossing. Okay, there. So that's another kind of glyph. And all these 3 diagrams project down to this shadow here. I think shadow was I don't know if Lou, did you invent the word shadow? Don't know. Anyway, you can't talk anyway. So, so I want to sort of make that definite. And if you look at the next figure down here, instead of putting a glyph on the crossings, I've just labeled them with A and B and then an A bar. A bar is meant to be the opposite of A. So if that was a real crossing and say this was positive, then this one would be a negative real crossing. Okay. And B could be something else. It could be the virtual crossing, could be a welded crossing, could be anything. Okay. And we have So that's the idea of representing generalized knots, okay? And what can we do with the generalized knots? Well, we use your Reidemeister moves, okay? So R1A means that we can have a little monogon here, and the crossing is labeled by A, and that can be undone, or perhaps not. And then we've got the R2 moves, and they're divided into two. One where the arcs go in the same direction. They call that, let's say, a parallel R2. And one where they go in opposite directions, a non-parallel R2. And it's important to distinguish between those two because they have very different properties. And then there's an R3, which obviously involves a trigon, and it moves. The appearance seems to be of this arc moving across this crossing, but that appearances are deceptive. You could say that this arc is moving over this crossing, and so on. There's those three interpretations of the R3. Okay. Right. Now, with a generalized knot theory, you have these various tags, A, B, C, whatever, and they will have certain properties in the sense that some of them might obey R1 or maybe not. Some of them might obey R3, but for instance, doodles don't. So that's the start of defining a generalized knot theory, so far with only one kind of tag, all right? We'll introduce more tags in a minute. So now if we go to this is a table. So there's all sorts of various generalized knots, okay? So there's the shadow, and that doesn't satisfy any of the Reidemeister moves at all because it's dead, right? Can't do anything, it's stuck, right? Flat just obeys all the Reidemeister moves. The ribbon, on the other hand, satisfies R2 and R3, but not R1, because that would introduce a kink in the ribbon. The doodle satisfies R1 and R2, but not R3. And so on. There's virtual, which is got a tag of V, and the weld, which looks very similar, W, it's got the same properties here individually. And then there's something called a free knot, which I might go into later. Homotopy knots, which are neither positive nor negative. Of course, there's real and negative real with R and R bar. And then there's singular, which has two sorts of glyphs, a black dot or a white dot. And the white dot is the inverse of the black dot. And you notice I've grouped those into two-dimensional and three-dimensional. Now, what does that mean? Well, you may have guessed already, but two-dimensional means that each tag is its own inverse. Okay, so for instance, W bar is the same as W, and so is V bar, and so on. Whereas the three-dimensional ones, and as far as I know, there's only two of them, real crossings and singular crossings. They have distinct inverses. Okay, so they're three. There I'll call those three-dimensional, right? And something you will notice is that everything except the shadow, which doesn't satisfy anything, they all satisfy R2. So that's a kind of universal property. Everything seems to have that. Okay, so that sums up what you can do with a diagram in the plane where there's only one kind of crossing, only one kind of tag. But of course, that's not very useful. We have to introduce the idea of dominance. So here's, now we've got two different tags. Well, they may not be different. It's quite possible for A to be equal to X. But anyway, X dominates A if I can move an arc, which is labeled XX, over a crossing labeled A, as I've done there. I mean, I know you just have to imagine that's moving over A, okay? So that's what I mean by dominance. And I have a little table of dominance here. Not everything is filled in because, well, I don't know whether we go to some of those. I mean, anyway, the virtual, you see, virtual dominates everything. It doesn't dominate weld because you don't have virtuals and welds in the same diagram. And so does welds. They dominate everything. Now, if you go to reals, you see an interesting fact that the positive real dominates the weld. Okay, that's why the weld is different from the virtual. Okay, so, and of course, reals dominate themselves, and they obviously dominate singulars and the two singular tags, as does the negative real. But the negative real does not dominate W, as we know. It's only one of them which dominates. If you had both of them, then you'd get a trivial knot theory. Okay, so that's the idea of a generalized knot theory. And here's a picture of virtual sliding over X, okay, or past X, or whatever you like to think. Virtual tags dominate all. Okay. So now we're going to make a definition. A knot theory is regular if R2 is allowed. But we saw on that set up the table that everything's regular. I mean, except shadows, but you know that they don't satisfy any R moves, so you can't. You know, that's the only possibility. Now, a knot theory is normal if it has a dominant tag. So classical knot theory is normal, as are all virtual theories. Planar doodles are not normal. Planar doodles, because they don't have the R3 move, you can't possibly talk about them being normal because there's, well, you can't. But on the other hand, virtual doodles, where instead of doodles being on a plane, they're on an orientable surface, they are normal. Okay, so because you've got the virtual crossing which dominates the doodles, the doodle crossings. Okay, so that splits. Or I should say, a knot theory. Well, technically, a knot theory is normal if it is regular and has a dominant tag. But since they're all regular anyway, that's irrelevant. So where do we get to? Right, a knot diagram is annular or braided if it's the closure of a generalized braid. Okay, here's a generalized braid. I think you can guess what a generalized braid is. It looks like an ordinary braid, except it's got different types of crossings according to the theory, all right? And you can close this up and make a knot in the theory. Okay, and now, so what theory we got? Here we got Alexander. Every knot in a regular theory can be represented by a braided diagram. Oh, and I should say at this point, I can write things, can't I? Somehow. What's this? I thought I could write with this. Maybe. Anyway, I should say that this is joint work with Bartholomew, Andy Bartholomew. Okay, so I thought you could write things. Okay, maybe not.
You need to go out and come back in on it with a different share screen with the
Do you?
pen. Yes.
I
think so.
Okay, all right. Never mind. Anyway, every knot in a regular theory can be represented by a braided diagram. So you take a knot in a regular theory, and it's obviously got a representative as a diagram, and then you can make that diagram braided. Okay, and the proof is surprisingly simple. So how do we do this? We here's a crossing, right, in this braid theory with tag A, and you replace that by continuous line here, and a solid bridge labeled by A, and and then you make Seifert cycles. So these go off, they become cycles, they're all disjoint. So some of them are nested, some of them are not nested, some of them are joined by these bridges, whatever. And then we can consider what's going on. Because a cycle is oriented, it's, and we're on a two-sphere, by the way, it's the boundary of a right-hand disk, if you like, where you go round the cycle and your right hand points towards a right-hand disk and your left hand points towards a left-hand disk. Okay, so it divides the sphere into two disks. A pair of cycles divide the sphere into two disks and a separating annulus. So if both cycles are oriented in the same direction, that is, they're homologous cycles in the bounding annulus, then they're called a coherent pair, all right? Otherwise, they are incoherent. Rather like me, I need a drink of water. Note that if two cycles are joined by a bridge, like here, then they are necessarily coherent. And the annulus between a coherent pair is the intersection of a right and a left-handed disk of the pair. Now we've got a little number, which is H. H is the number of incoherent pairs of the Seifert graph obtained from the diagram K. If H equals 0, the diagram is braided. So that's a real useful way of deciding if a diagram is braided. And it is isomorphic to a diagram in which the cycles are circles of latitude and the bridges are arcs of longitude joining cycles. In other words, it's the closure of a braid. And notice, if H is 0, then there are two polar regions. You know, there's a northern pole and a southern pole. I don't know, let's say the northern pole is the left hand and the southern pole is the right hand disk. Okay. So as we saw earlier, an R2 move can be divided into two kinds. If the arcs are oriented together, say from left to right, then there's a parallel R2 move, and we denote that by R2 dashed. And these preserve the value of h. If the arcs are oriented in opposite directions, then this is a non-parallel R2 move and is denoted by R2 double dash. These change the value of h. You see, this is why I needed to distinguish between the two types of R2 moves. And these are further divided into two types. If an R2 double dash move involves the arcs from two distinct cycles, then we call this a Vogel or V move. Otherwise, it's a non-Vogel move. So Vogel moves are quite important. And we have a lemma here, which you can easily check. A Vogel move, which creates a bygone, in other words, a creative Vogel move, decreases h by 1. So if h is n, we make n Vogel moves, and lo and behold, h is 0. And we've done the proof. We've made this Alexander, or this generalized Alexander theorem work. Okay, now the other theorem would be a generalized Markov theorem. So we have, supposing we have D1 and DQ be diagrams in a normal theory, which are braided and represent the same knot. Then there are a sequence, or is a sequence? I don't know. There is a sequence, perhaps, of local moves on braided diagrams, D1 to D2, D2, so on. So all these we get from D1 to DQ via braided diagrams. Okay. Obviously, you can get from D1 to DQ by non-braided diagrams, but we're saying that you can get from D1 to DQ by braided ones. And what are these moves? Okay. Well, here's one of them. This is the fourth Reitermeister move. These turn up in various theories. One of them is it just interchanges A and B like this, and that, for instance, if you've got, for instance, in a free knot, you interchange a virtual crossing with a flat crossing. Okay, and that's allowed. And that's how you, that defines free knots for those of you who are interested in free knots. Or when you do the swap over, you could invert B. That, for instance, happens with Kaufman's virtualization. Okay, so you have, say, this is, say, a real crossing here. This is a virtual crossing, and you move this, you swap the two, and say a positive real crossing becomes a negative real crossing. That's part of the virtualization move. And then there's this one, which is an exchange move. So we've oriented it in opposite directions here, and we've got an A and an A bar, and then that we throw away the A and the A bar and replace it by a B and a B bar. And if you think about it, you can always do this because this is ready to do a non-parallel R2 move. You can do this, that eliminates A and A bar, and then you go back again, but this time with B and B bar. So it doesn't appear to be anything new, but it is new when we look at braids. So, so that's called the exchange move, and we'll be coming back to that in a minute. So, right, the Markov move. Okay. So an R1 move creates or deletes a monogon. A creative move R1 plus, and a deleting move R1 minus. The new monogon is a new cycle, okay, when we create the Seifert cycles, and is coherently oriented with its parent cycle. So a parent cycle gives birth to this new monogon. It's joined by a bridge, so they're both oriented coherently, and the value of H is increased because supposing if H is positive, then there's somewhere there's a cycle which is incoherent to the mother cycle, and of course when you give birth to this new cycle which is oriented coherently with the mother, it will be incoherent with the other one, okay? But that doesn't happen if H is originally naught and the new cycle lies in one of the two polar regions, okay? So this special R1 move is called a Markov move. So the story is that an R1 changes H unless we know that H is already 0 and the new cycle lies in one of the, or the new monogon lies in one of the two polar regions.
Rod?
Yes?
Can you go back to the 4 move for just a moment?
Yeah.
In the first two, those
Yeah.
are either coherent or incoherent orientation. Is that correct?
Yeah, I haven't bothered with orientation. I don't think it's relevant in this case. It's only relevant here.
Okay, thank you.
Okay, so that's something which, so moves in a regular theory which preserve H. Well, there's the Markov
Can you
move.
quickly remind us of the definition of H, Rod? I must have missed
H
it.
is the number of incoherent cycles.
Okay, thank you.
The number of cycles which are oriented in opposite directions. So the number of pairs.
Got it.
Yeah. And then the moves in a regular theory which preserve H are, well, the Markov moves, parallel R2 moves, parallel R3 moves. I actually, if you remember when we went back to R3, all the arcs were oriented from left to right. That's fine. You can always assume that's the case. And R4 moves, okay, including the exchange move. So these we will call the R0 moves. So what are they in terms of braids? Okay, so here's a braid, a generalized braid. It has things coming in, things going out, and we make it slightly bigger by putting this A here. Okay, and you can see this is a Markov move because if you go round and join them up, that's an R1, you know, with A on the crossing, and it doesn't change H. It's still, well, you can see it's still braided. Okay, when we close that up, it's the same knot as this one, right? And then here, the moves 2 and 3, which we talked about before, they're just braid moves, so they're included in the group, okay? And they include conjugation. Now, this is what an exchange move looks like on the top. It could be on the bottom as well. But what you're doing is you've got these two braids, say in BN, and then you add an A bar here and an A, and you convert the A bar to a B bar and the A to a B. And if you think about it, the closure is the same knot. And that's the exchange move, which exchanges A and B. Right. Now, the moves in a regular theory which change H, now by a sort of preparation lemma. The only moves we need to consider which change h are R1 moves when h is greater than 0 and V moves. Okay. And there's a little bit of definitions here of notation. A sequence of R moves which go from K to L of length Q will be denoted by this. If the moves do not alter HK, we write a little naught above single move or a naught above this sequence of moves and refer to them as H neutral moves. A single R move which raises or lowers H is given by this symbol here, K up arrow to L or K down arrow to L. The maximum value of H in a sequence is denoted by H of this sequence, and it's the maximum value of H, I equals 1 up to Q. And then a little sequence where it goes up and then down is called a simple peak or just a peak. Okay. And then a couple of lemmas will do the job. So the peak condition says, supposing we've got a little peak like that in a normal theory, it has to be normal, then one of the following is true. K is isomorphic to M, okay, or there's a sequence from K to M such that the height of this sequence is less than the height of L. In other words, you're pushing down H all the time. And then there's the transport condition. So supposing K goes up to L and then H is constant from L to M, then one of the following is true. Maybe the moves can be interchanged. So K goes to L without raising H and L rises to M. I think L might have to be a different L, but anyway, you see what I'm trying to do. I'm replacing an up arrow and a level arrow with a level arrow and an up arrow. Or there is a sequence from K to M, and it goes on that, so there's a sequence to LQ, which then goes up to M, and the maximum value of H in that sequence there is less than H of M. So now I think you can all see how the proof of the generalized Markov goes. You see, if H increases at all from 0 and then back down to 0, somewhere along the line there's a plateau. All right, it might be a little peak, but it could possibly go up, go along, and then down again. In which case, by the transport condition, we can push all the ups to the right. And eventually we get a peak. And then we can apply the peak condition, and we've reduced H. So we keep doing this one after the other, and eventually the sequence going from K to L is has all H0. Okay. So that's, of course, I've left out the details of this, but it's in our paper, so which I could put perhaps into the general section. Okay, so let's have a look again at generalized braids. Okay, this is sort of notation really. This is a standard generator for a generalized braid. Instead of having, say, a real crossing or a negative real crossing, you just have an A there, okay? And you denote that by AI, okay? And you've got the cubic relation here, which says that AI CI minus 1 BI is BI minus 1 CI AI minus 1. And in practice, there's, you know, B is always equal to A, or C is equal to A, or something, you know, but you don't usually have three distinct ones. But anyway, that's the most general situation. And anyway, this comes from an R3 move, and we'll write this R3 move as R3 AB semicolon C. So C occupies a sort of middle position. It always stays in the middle, and A and B swap round about C in this move. So that's why there's a semicolon there. Okay, now
that move is directed, is it not?
yes, yeah, they all go from left to right.
Okay.
Yeah. And then, so supposing we've got braids in a in a generalized braid group BNK, where K is some knot theory, and let's see, A and B are tags in K, then the moves are, so I'm assuming it lies in a limit, so I can multiply alpha, which is in BNK, by AN, which is in BN plus K, you know, the usual Markov moves. And in this one, I'm raising alpha up a bit, so I can multiply by A1. Okay, so this is stabilization or Markov move. Then we've got alpha goes to beta alpha beta inverse conjugation. That's the usual one. And then we've got the exchange move, okay, which I've written like this, where we swap alpha, we swap A for B, okay, and that's the exchange XAB. Now, unless you've looked at these generalized braid groups, you probably didn't know there was such a thing as an exchange move, and in fact it's not needed. You see, for classical braids you don't need this exchange move, and it was proved in terms of the other moves by Trapzik, but presumably other people have proved it. I don't know, but it's in this publication here. It's also known that we can interchange R bar and W. R bar is the left-handed real crossing, and W is a welded crossing for welded knots, okay, and we don't need that. In other words, we don't need an exchange move for welded knots, but the interchange of R and W is independent for virtual knots. So Saiichi Kamada has defined an invariant which shows that this exchange move is necessary, and we can get around all this by the following proposition. So consider a regular knot theory with tags ABC. If the following four R3 moves down here is allowed, then the exchange move XAB can be written in terms of the other moves. So provided these moves are allowed in the theory, we don't need to consider the exchange move. And this shows how you get from alpha AN beta AN inverse to alpha BN beta BN inverse by putting these in, and you can have fun checking that that is so. Right, and now this implies for real braids the exchange XR R bar is a consequence of the other M moves, and you just put A equal to R, B equals R bar, C equals R bar, and then that works. For welded braids, this exchange R bar and W is a consequence of the other M moves. We put A equals R bar, B equals the weld, C equals the weld. So that's why it works for welded braids. And as I say, Saichi has shown that for virtual braids, the exchange move is necessary. You can't do without it. Okay, so that's an interesting fact. Right, well, what about doodles? You see, doodles were the only example of regular knot theory, which is not normal, okay? So the associated braid group with doodles are called twins, okay? So they have generators d1, d2 up to dn minus 1, and relations, of course, the usual ones. They commute if they're far enough apart, and di squared is 1. That's all, and there's no triple relation at all, no cubic relation, because they're doodles, okay? So, and because of that fact, it's very convenient. It means that doodles have a unique minimal diagram with no monogons or bigons. And because they're regular, they can all be represented as the closure of a twin. And I was going to do a picture of these two doodles. But I could do this last week, but I can't do it now. I wonder if I make that mega. I wonder if that makes a difference. Nope. Okay. All right. Just a mystery. Anyway, I didn't draw a picture of the poppy. I'm sure you know what a Borromean doodle is. But anyway, it's the closure of this twin here. Here's a doodle, and it is minimal. It's minimal because it doesn't have any bigons or trigons. Sorry, bigons or monogons. But it's not braided. Okay, it's not the closure of a braid. So what can we do then with doodles? We would like to prove some kind of Markov theorem for doodles. Well, we need a new move, okay? The augmented Markov move is defined by multiplying a twin by the following, these two twins here. So this is tn minus 1 all the way down to ti and then back up again. And this one is t1 up to ti and then all the way down again, okay? And these are called, so if we multiply this on the right or the left, these are called augmented stabilization moves. And it's augmented because when I equals n or I equals 1, these are the classical stabilization or Markov moves on a classical braid. And so why do we need these extra moves? I should say, another odd thing is that I'm sure I had, I could acknowledge somebody called Gotin who's independently proved this. But anyway, and I thought I'd written it in. Okay.
Yeah, it was. It was a couple of pages up.
Was it?
There you go.
What? Oh yeah, Gotin. Yeah. Okay. I'm not going mad. No. Well, not that mad. So why do we need this augmented stabilization move? Well, think about the problems, okay? First of all, note that if you multiply by one of these, it doesn't change the knot, okay? That's the easy bit. But why do you need it? Well, you see, when you go to the original proof, So supposing you've got two twins, D1 and D2, supposing they close to the same doodle, then they're related by a sequence of the usual moves plus the augmented Markov move. And so this is a kind of an explanation of why it's necessary, you see. So supposing you've got a braid here and it's closed to make a braided diagram. And now suddenly you introduce by an R1 move a little disc here in the it's not going to be a Markov move because it's right in the middle of this braid here, okay? And you normally what you do with a normal theory, you push this little disc, this little monogon, all the way out to here, and then it becomes a Markov move, okay? But you can't do that with doodles because you're not allowed to do an R3 move, you see. You're not allowed to create a triple point. But what you can do is to create a double, you can do lots of R2 moves, and then when you've got this arc up here, it can then go round infinity, and then this braid here is one of these. It's SNI. You see, you got TN here, and then blah 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 blah, all the way down to TI, and then back all the way up to TN again. Okay, so that's sort of an idea. And once you've got that, you can look at the previous proof and see where you need it, and then it works. Okay, so and I've said that it's necessary. Of course, maybe there's some clever way you can get rid of it, but there isn't, because if I take this twin D1 D2 squared, this closes to the trivial doodle, but it cannot be reduced to D1 by the usual moves. The new move is necessary. So I take, this is D1 D2 squared, I multiply it by D2 D1 D2. Okay, that's one of these S's. And now I can start cancelling, you see. D2 cancels with D2, D1 cancels with D1, D2 cancels with D2, and I'm just left with D1, which is obviously the trivial doodle. And so, but why do I know that it cannot be reduced to D1 by the usual moves? Well, I have to invent some sort of invariant, and I don't think I'm going to define it now, but it is in the paper, and which I'll give to Lou to put in the bookery. Right, well, that's basically all I want to say. So I've finished early. Are there any questions?
Here's a diabolical suggestion. What would happen if you of course have labels for vertices which are in different kinds of theories? What if you allow the theories to mix according to the labels, so that in one region in the knot would be welded, but another place in the knot would be virtual? And of course, you're going to have to ask what would happen when virtual labels interact with welded labels, but perhaps they just don't interact.
Well, I've always assumed that they couldn't mix, but I mean, who knows?
It's the devil's suggestion, yeah.
Yes, you can experiment with that if you like, Lou. I have no idea what would happen if a virtual meta weld. Would it explode in a puff of non-logic, or?
That sounds like a good suggestion.
Yeah.
I think it's great to have this Markov theorem done in such a nice generality. That's really cool.
I think that's as generalized as you can get, but who knows? As I say, the only theory I know about which isn't normal, and so you can't do it, are planar doodles, and then you've got this extra move, and that does the job. So, and of course, it's interesting this this idea of an exchange move, which I'd never really thought much about that before, but because it doesn't occur with classical braids, but for you know, the virtual braids, you need it.
Yeah, of course, we got forced into that. Another thing is when you work with the classical Markov theorem, of course, you get really nice formulations for invariance by finding out what you can do with the Markov move and so on.
Yeah.
It seems harder to handle this situation when you're facing exchange move and other things.
Yes, I know that Dornois used the exchange move a lot in his work, because I can't remember why, but I mean, he was looking at classical knots, maybe something to do with the ordering or something. I don't know. Yeah.
So, for example, what happens to the Hecke algebra structure if you try to do it via in virtuals?
I don't know.
Yeah.
There's lots to do. There's never going to be any shortage of problems.
Roger, I had a question about the transport condition.
Yeah.
So can you put your slides back up? I don't
Sure.
remember. So just where the transport condition is defined.
Okay. This one?
Yeah. So why isn't the original three-term sequence KLM, why isn't that an instance of the second type?
Well, because we're making the up arrow go so that the top of the, so the up arrow goes to M. It goes, you see, it's easiest to look at this. If you can just exchange it like this.
Oh, so you're saying you put the increase at the end?
Yeah, that's the idea. You try and put all the increases towards the end, and then you're necessarily going to get a peak.
Yeah. Okay.
So that's the idea.
Thank you.
Are there any other questions?
So, I guess, go ahead.
Sorry. Sorry, somebody said something.
Yeah, am I audible?
Yeah. Right.
Query with the messages available here. So could you please go to page 12?
Page 12. Okay.
Yeah, page 12 of your slide.
So this one?
Yeah, thank you. So we took the strand and see the braid from top to bottom. So we took the strand to the right of the braid beta in figure 14. We could have taken the strand to be on the left of beta as well. I mean, if I write it algebraically, I can have right stabilization and left stabilization. For example, in doodles,
yes, you could, but then you see, it doesn't make any difference, because if you're going to close this up, you can move this A all the way around so it starts at the beginning. So you're quite right. You could have it on the left instead of the right. Doesn't matter.
Yeah, but
You
then
know, if you can do it on the right, you can also do it on the left.
yeah, but what I'm trying to ask is that if I'm doing it from the right, then I should be able to use these moves to get to the left. I mean, for example, in doodles, we took these augmented
yeah,
moves.
but the move you would use would be conjugation. You see, that a conjugation will take this over to the left. So that's that move would change it to the left. Yeah, and of course, I forgot to do it. Well, I didn't do it on the bottom. I suppose that may be necessary to do it on the bottom as well. But
Okay.
yeah, does that answer your question?
I guess. Thank you.
Okay.
So I'm presuming that this is based on Vogel's theorem or version of the Alexander copy.
Well, it was Vogel's paper in the Commentari Helvetici, where I think he proved the Alexander theorem, but of course that was just for classical knots, right?
Right.
But you know, his method can be generalized easily to any regular theory. So you know, I owe a debt to him. That's why they're called Vogel moves, or Vogel. I don't know. Is it Vogel?
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 I think it's Vogel.
Vogel. Okay. I will from now on call it Vogel moves. Okay, so are there any other questions?
Thank you,
Good.
Roger.
It's my pleasure. Now, Lou, you're going to talk Tuesday?
Yeah.
And Lorenzo, you're going to talk next Friday? Excellent. Okay. I'm wondering if that would be a good place to stop and have a summer pause. Don't know what you think.
We could.
I know Liz wants me to go down to a cabin without any without any Wi-Fi.
What did you have in mind? Perhaps start again in September?
Something like that, yeah.
Yeah. Mm-hmm.
If there's sufficient, you know, people want to continue. I mean, I think Vladimir ought to give a talk sometime.
Good.
Okay, so enjoy the weekend, everyone. I'm going to stop now, and I think Lou and Sam, we might have a chat on Sunday. Is that right?
No, wait a minute. I'm very busy on Sundays.
Okay.
I would really like to do this on Friday if we could, but you can't. So let's discuss timing.
Friday is no good because that's today. But it, you know, I could wait till next Friday. Or what about you, Sam?
I think I'm flexible, but let's see. Let's see. Friday's a little hard for me.
Yeah. We could have
I guess I would. I'm getting an echo.
We could do it
I
on
would
Tuesday.
prefer to just shift to next Friday,
Yeah.
What time would that be?
immediately after the talk.
Oh, okay, I can make that.
Okay. Yeah. I think Brian has vanished.
No, I'm here. No,
Oh,
there,
right.
there.
Would that be okay?
Yep,
Mhm.
yep.
Okay, in a week's time then.
Okay, good.
Okay.
And then on Tuesday, the next talk by Lou. And then on Friday, Lorenzo. Okay. So, as I say, have a good weekend, everyone.
You too.